today's episode, we speak with Tatsu Hashimoto. He is a Stanford professor and AI researcher behind some of the most exciting open source AI projects, including Alpaca and AlpacaFarm.
AlpacaFarm was our attempt at building this simulator that allows us to basically run the whole pipeline of going from a base language model to a fully tuned final language model, and we can understand the impact of data, the impact of reinforcement learning, and so on.
We talk about how large language models contain biases and reflect people's opinions.
When there's this instruction tuning in RLHF that happens, you start to see a shift towards higher educated, higher income, generally more liberal opinion viewpoints. And we thought that was kind of an interesting observation.
And of course, we hypothesize about the future of AI.
If you had to take a bet given what you know now, where do you think this goes?
I think it would be maybe similar to oligopoly. There will be a couple big LM providers. I think they will provide differentiated products. I don't necessarily think that there's going to be a single LM to rule them all.
Thank you so much for joining us. I hope you enjoy this episode. Tatsu, thank you so much for joining us.
Great. Thank you very much.
It'd be awesome. Can you tell us a little bit about your kind of journey to Stanford and where your research is focused now?
Yeah. So my original background is in statistics and actually computational biology during my graduate school at MIT. And there I was really focused on trying to understand a lot of aspects of the cell, like, how does the genome, shape us during development and so on. And so that entire time I was really interested in sort of understanding deep complex systems. And a lot of that is reflected in the research that I do today, which, in a funny way, large language models are also these very large complex systems that we are trying to understand and reverse engineer. And the works that you mentioned very much go in this vein of like, can we build tools almost like informed by my background, thinking about model organisms? Like, can we build smaller models that display many of the behaviors of these large complex systems that are changing the world today so we can study and improve them? And so that's kind of my original journey. I started out in statistics and computational biology, and I was really interested in things like decoding the language of the cell, as well as when I came here to Stanford for a postdoc, decoding sort of meaning in human language. And I got very much involved in language generation, pre-large language models.
Cool.
But then, as sort of the field evolved, it became very clear that language generation, like generating text, was going to be intimately tied to broader problems in machine learning, and now everyone calls it AI. And so that's the area I operate in now. It's sort of this organic transition from language generation to large language models.
Awesome. Yeah, it's really interesting what you mentioned about kind of building smaller systems that model the behavior of bigger ones. And I feel like that's been one of the things that really captured everyone's attention about Alpaca was just, that model, even though it was smaller and more lightweight and kind of tuned on less data, had some incredible performance. Maybe can you talk a little bit about kind of the origins of that project and what you've learned since then?
Yeah, so the origins of the project, I guess we'll talk about Alpacafarm a bit later. But Alpacafarm was originally the high-level thing we were interested in, essentially replicating, at least in like the sandbox, the entire training process for a large language model. So we could tweak all the different pieces and then understand how, which parts are important, which parts require improvement or can be improved. And as part of that, we were trying to do the very first step of building an instruction following model. And we were sort of fortuitous that, Llama sort of released at that time, at least to us academics. And we basically were preparing sort of the training data for it by doing this sort of synthetic data generation from Text DaVinci 3. And so we had all the pieces in place right when Llama was released, because we were already trying to do this project of understanding large language models. Our original plan was actually to do the whole thing with OPT and FLAN-T5. But what we actually found was, probably like yourselves and everyone else, if you do this with Llama, the behavior feels qualitatively very different. And when, Llama was released to us, it was actually very much a side thread. One of my students was like, oh, I'll go, get the permission to use Llama. I'll train it and we'll just play with it a little bit. And then we played with it a little bit. And then we found, wow, this thing is actually really good, or at least, it behaves in a very different way from our interactions. And so we really felt like releasing it and telling everyone else in the research community about it was going to be something that would be appreciated. And so we went and did the blog post and the demo and all of that, because it felt pretty different from a lot of the baselines that we were working with.
What made it different as a baseline?
Yeah, I mean, I think the experience that I think most people have had playing with like the Llama fine-tune models and everything else is that the Llama base model is just in some ways a lot better. It feels like because of maybe the coverage of the data, pre-training data that they have, or they explicitly do this non-chinchilla optimal training regime where they train a small model for much longer. So many of those pieces combine, I think, to make the base model a lot stronger. And then so when we combine that with a reasonable instruction tuning data set, you get nice behaviors back out. And of course, there's been, much better models since. And we know that, a small amount of instruct tuning data doesn't get us all the way to GPT-4. But I think there is really this sort of gap between sort of a lot of the prior base models that came and then the Llama-based models. And then now, of course, the next generation of models that are hopefully soon going to be coming out.
Yeah. And I think it'd be super interesting, maybe for our listeners, just to contextualize, what is the quality of performance today from, models like the Alpaca model? I think obviously, I feel like in the months since you've released it, there's been a lot of folks interrogating, what can these models do? What can't these models do? You've had publications out of places like Berkeley where they're like, look, maybe you can mimic in style, but not in substance. Like, where would you kind of categorize the state of performance of these models today?
Yeah, I would say that the models are slowly but surely sort of creeping up towards the ChatGPT performance. I think the real challenge here is evaluating these systems is very complex. One thing that I think is very much underappreciated by maybe everyone that's not a academic carefully studying these systems is that ChatGPT and GPT-4's like sort of domain on which they have coverage, I think is much wider than what a lot of the open source people have been targeting. And sort of also a lot of these systems are targeting not just conversational settings where you just, a person just comes in and types in random stuff, but also a lot of the benchmark tasks, like knowledge intensive tasks, like, like trivia QA style things where you have a one-word response to a question. And because, OpenAI probably has a much wider tail coverage, like these kinds of disparate domains than the open source, evaluation is very challenging. If you have a conversation with, say, the leading open source systems that exist today, you might think that it's very close to ChatGPT. If you start going out in the tails and saying, oh, can we productionize a sentiment classifier using these systems, you might find that there's a very big gap, right? And so, that was a long answer to your question, but I actually think, if we're thinking about the head of the distribution in terms of chat applications, a lot of the open source systems are getting close. If we think about fine-tuning is really good at the locations where you're giving it data. Everyone's generating data for conversational applications. That's getting increasingly good. All of the tail stuff, like, is it good at answering very detailed questions? Is it good at writing very specific kinds of essays or limericks or something? Those kinds of things may be, going to require a lot more effort. And so I think there is sort of definitely a kernel of truth to both the open source people who are pushing on just like, let's fine tune harder and more aggressively and more efficiently, as well as sort of the imitation learning paper, which is saying like you can't go all the way with fine tunes. I think the reality is probably you can push fine tunes quite far, but there's strong diminishing returns, and people need to be prepared to pay essentially large compute costs and data costs to go the rest of the way if they want to keep pushing that agenda.
Super interesting. And so do you think, like, as you think about, the next, version of these higher quality, lower cost to train models, is there a limit to how much you can kind of push through the reinforcement learning mechanism that you guys did for Alpaca and kind of outlined in AlpacaFarm? Or is there still, further optimizations to be done around that, where, you could imagine, having models that get around some of these like generalizability objections, but still are using kind of the reinforcement learning approach you guys did?
Yeah. So I think the key thing here is maybe to think about a data efficiency trade-off. Like, I think everyone likes to think about it in binary terms. Like, you can't fine-tune X, or you can do everything with fine-tunes. But that's not really the reality. It's who is paying the cost is the way I think about it. When you fine-tune a really, really good, really big base model, things feel easy because with a little bit of data, you're going a very long way. And that's because, in some sense, Meta has paid for the compute and data cost of making these models good. And if you want to take a, 13 billion parameter model and make it, cover all the different things that a 65 billion parameter model is going to do, you're going to be paying tremendous data and compute costs. So, no one's really been pushing this. Of course, there's been some works recently, like Orca and so on, that pursue more intelligent data generation strategies to try to get better fine-tuned models. But I think the point is no one's really done this, but if you really want to get there with fine-tunes, I think it's going to be a lot of data and compute cost. But I think the agenda could in principle be pushed. I would not be surprised if that was the case. It's quite clear, at least interacting with OpenAI systems, that they're investing very heavily in data collection and in fine-tuning, even like ChatGPT and GPT-4. I think the open source models are not even close to the amount of coverage and scale at which I think OpenAI is doing this.
Yeah, it makes sense. I really like the way of framing it around who is paying the costs. It's kind of like what you were saying. There's no free lunch for the performance of these models. Like you either start with a good model and then fine tune it and get performance that way, or you have to start with a less good model and then kind of incur the compute costs all the way up to that performance. I guess you're obviously much closer to it than we are, but I think from playing with models like Alpaca and Databricks Dolly, the performance was so, I guess, much better than I would have thought it would be. And maybe that's, because I don't know as much as you guys, but were you surprised by the performance of these kind of smaller models that were fine-tuned? Was that something that you and your group was expecting, or maybe, you were surprised by how good they actually were?
We were very surprised. We were very surprised by how it seemed to adapt to a diversity of tasks. Mm-hmm. In sort of our initial tests, of course, we expected it to handle things like question answering and maybe writing emails. But it would do, all sorts of weird stuff. It would write recipes, not good recipes at all, but it would follow the format of a recipe. It would, be able to attempt to write poetry. It would follow tasks that we thought maybe would be kind of out of domain for a lot of these systems. That was pretty surprising to us. The other thing that was very surprising to us was the amount of data that it took. Our very initial model we trained on this only used 10,000 examples. And that behaved quite well. And the final release had 52K, but actually that model didn't feel much better than the 10K one, which, suggested to us that really a lot of this was in the base model. And if you have a really good base model, just a tiny bit of instruction tuning model would kind of pull out the right capabilities from these systems. Going back to the who paid the cost, it was, I think, very much nice base model. You just pay a little bit of cost on getting it to follow instructions well, and you get these surprising capabilities. To give more context, though, we did play quite a bit with the OPT models, the previous generation ones. And that didn't rise, at least to us, to the level of, we should go and make a blog post. It really was when we switched to the Llama model that it felt like there was something there.
Yeah. The importance of that base model, that's fascinating. I guess one other question, because it seems like you and your group, you've shown that these kind of smaller models with a great base model can achieve really great performance, and it doesn't cost that much to fine tune them. And we've already seen kind of an explosion of those with Dolly. Do you think we're going to live in a world where there are kind of many smaller models, or it will lend itself towards that? Or, there's also kind of this one model to rule them all in the cloud. It seems like there's kind of the two camps of hey, the big players will do everything in the cloud, and one model is going to have all of this, they'll be really good at the head and the tail, as you were mentioning, versus, we're going to fine tune a model for kind of each different use case. Yeah,
I think that's, a really interesting, I would say, open question. I've heard many takes on this.
Yeah.
Things like, people don't want to let go of their data, so they'll have everything on-prem. I've heard arguments like, fine-tuning will be better because you'll have your own data. Or, the what's it called? The efficiencies of scale mean that you're going to be much better off using the big OpenAI model. And there's definitely truths to all of this. Some of them I am more skeptical about. With the cloud, certainly we went through the similar transition of no one would upload their data to the cloud, and everyone's now uploading their data to the cloud. I think that is going to be a slow and steady process. I don't think that's necessarily the thing that will make distributed LM sort of win out in the end. Where I do think distributed and like many different kinds of LLMs will win out, I think is this question of how much value there is to specialization and diminishing returns to scale. I think those two are very interesting questions. So to give a very concrete example, think about, say, like role playing again, or like, storytelling with a large language model. Those kinds of applications obviously very valuable. But OpenAI or some large centralized company that's trying to build one big LM to rule them all, that's going to be a little challenging because you want those systems to be factual, and having a factual system might conflict with a system that's really good at storytelling, which is sometimes about making stuff up. And so, of course, in principle, like people can kind of context switch, right? Like I can context switch from making stuff up to giving a very factual talk. But if it's hard for a language model to do that, then specialization starts to make a lot of sense. And of course, that specialization might happen at the vendor level. OpenAI might have like dozens of different models, one tuned for different tasks, but it would still be very much in the specialization direction. And if you take that to the extreme where, maybe everyone wants to personalize it because there's some slight conflicts, let's say in values or what we want from the LMs, then you might start to end up with sort of much more specific LMs at like the company level or like even the person level. So I think that's the question. Like, can you mix these different kinds of goals into a single LM? Or is it just hard to get that level, like very precise tuning to work? I think that's a really key question. And of course, the diminishing returns question, I think, is a really big one too. Whether a single centralized entity scaling up the base LM is going to continue to pay dividends.
Yeah. I mean, if you had to take a bet given what you know now, like what do you kind of, where do you think this goes?
I think it would be maybe similar to like a oligopoly. Like I think there will be, a couple big like sort of LM providers. I think they will provide differentiated products. I don't necessarily think right now that there's going to be a single LM to rule them all. I'm kind of skeptical that you can balance, let's say, creativity and factuality really cleanly. A lot of the interventions I've seen on the academic literature really do give a trade-off on that front. And so I imagine many different models offered by companies sort of attempting to differentiate their products. And I imagine there will be an open source community that's like 1 to 1.5 generations behind, sort of on the basis of like models that these companies sort of like release back to the wild. So that's kind of the ecosystem that I imagine longer term.
Yeah. And what about like companies training their own models? Like obviously the news of today, I guess, with the Databricks Mosaic acquisition seems like a bet on that. Right. What do you think of that kind of future?
Yeah, I mean, I think that's a really interesting one. One thing that I think is really unknown is how much pre-training data affects large language models. The cost of training large language models and doing science on pre-training means that I think that area is probably under-optimized, even by the really big players. You don't get many shots to sort of retrain models. In a way, I think the wins from these companies might be if one of them discovers really nice ways of dealing with that pre-training data curation, they might start to get really big gains in differentiation from their competitors. Otherwise, if it's fully commoditized, I think it's in some sense a race to the bottom. Who can deliver the 60 billion parameter model for cheapest kind of thing. And then it's kind of hard to see where, in some sense, the value proposition is, other than, open source goodwill or something.
Can you say a little bit more about the kind of pre-training process, I guess, that you were alluding to, like what would go into that, and how that might differentiate the model?
Right. So I guess in the simplest, most basic flavor of this, you would have, your data mixture, a big web scrape, many different mixes. You would presumably go collect like Stack Overflow and GitHub and all these sources. I don't know for how long people will get to do that given the tightening data restrictions and all of this stuff. But you would have all of these corpora. And then there's the question of like, how do you filter some of your messier data sources? How do you weight all the data sources? Because you take multiple passes over the higher quality ones. And then there's also the question of like, how do you do things like tokenization to sort of advantage or disadvantage certain parts of your data set? There was that recent, I think OpenLlama was the one that used the tokenizer that collapses multiple spaces into one. And so it was not very suited for code, right? And so you might have things like this where, your tokenizers might need to be optimized. And so there's all these low-level details that in some sense like shape the base LM that you get out on the other end. And there's a lot of speculation about what people did right with Llama. And some of that might be data set. Some of that might be their choice to train longer on a smaller model. Some of it might just be they executed better. It's hard to know without the full details. But I think there's a belief that the pre-training data mix is a really important part of this process.
Fascinating. That's super cool.
One thing I definitely want to make sure we hit on is, obviously the Alpaca farm work you did. Maybe before we dive into our specific questions, would just be helpful if you could summarize that work for our listeners.
Yeah, great. Alpaca Farm is this, I would call it a simulator for the entire large language model training process. At least as sort of researchers, one thing we found to be difficult was to try to understand which parts of the large language model training pipeline really matter, right? You hear things like, the instruction following data really matters. You hear other people say, it's reinforcement learning that matters. And some people might even say, it's the reinforcement learning algorithm that really matters, right? And the kind of unfortunate thing is that because all of this work is being done behind closed doors, we have, in some sense, very little understanding of which of these pieces truly matter. And so Alpaca Farm was our attempt at building this simulator that lets you simulate the whole process. So you take a base language model, you train it on instruction following data in the same way that you do for Alpaca, and then we have a simulated human annotator that gives you like thumbs up, thumbs down ratings for model outputs, and then you can do reinforcement learning on that to do the RLHF process. And so that allows us to basically run the whole pipeline of going from a base language model to a fully tuned, final language model, and we can understand, the impact of data, the impact of reinforcement learning, and so on. And that was basically the Alpaca Farm project.
Yeah, and I guess I feel like this is a big question, right? Of like where do the improvements in models come from, right? Is it the underlying data you're feeding in, the quality of or extent of reinforcement learning you're doing? Like what is kind of given the work you guys did, like where'd you end up on that?
Yeah, I mean every piece is important, but if we were to say try to prioritize which ones are most important, the base LM is really important in the sense that that's where a lot of the knowledge and stuff is coming from, at least in the current tuning pipeline. We're not giving it enough instruct data that's really, changing the underlying knowledge store of the model. So the base LM is handling a lot of that. The instruction following data is the next most important. So the supervised fine-tuning step that happens right after, that turns out to be, at least from our analysis, the second most important, because that's what makes it, that makes the model do roughly the right thing. And the reinforcement learning, it turns out, does have a substantial impact. Like it's not zero. But the way in which it has impact is in some ways subtle. We found that it's able to do things like control the length of the answer or control how often it uses lists or not. And so it's doing, you might call it fine-tuning of the answer structure on top of what the model's already doing. And in prior work, before we did the Alpaca Farm, one interesting thing we found in some of our work on summarization is when you ask people to write a high quality summary, they'll often write very sophisticated text. They'll take the article, they'll paraphrase it, do all this stuff. But if you ask people to rate which summary is better, they actually want passages copied from the text because it's easier to read. And so there's this really interesting mismatch between what people will write down as what they think is good and what people will rate as being good. And reinforcement learning tends to close that gap, which I think is a very underappreciated thing that people haven't really talked about. People kind of think about humans as rational agents. Of course you're going to write the thing that you think is best, but it turns out that's not necessarily the case.
That ranking that you outlined of, I guess, the importance of, the raw LLMs, the supervised fine-tuning, and then the reinforcement learning. I imagine, obviously, there's probably some, when you were getting into the nuance of the problem you're trying to solve or the domain you're going after, how do you think about, I guess, to the extent to which that ranking changes based on what you're trying to do?
Right. Yeah, I think, that ranking changes based on, in some sense, how much generalization and extrapolation you want from the system and how much data you're willing to throw at it in the instruction following step, and how much compute you're willing to throw at it on the reinforcement learning step. One way to put this is, in some sense, instruction following data, the supervised tuning, and reinforcement learning, in the limit of infinite amounts of compute and data, they can compensate for each other. Supervised fine tuning can make the model do almost whatever you want. That's classical machine learning, right? Take your model and just throw a lot of data at it. Reinforcement learning is also in some sense the same, right? In the same way that you can do RL for robots from scratch and so on. You can just have the reinforcement learning policy take you all the way to a high performance system. But really, it's once again the question of like cost effectiveness and what system you get at the end. If you train for very task specific things using instruction following data or reinforcement learning, you end up with a somewhat brittle system. It doesn't generalize quite as well. Whereas if you're relying on the base LM and then tuning it very little, in some sense, because you're not using that much data, you're not overfitting the task. And that lets you generalize a lot better. That's been actually a very interesting lesson from a lot of the other machine learning work, like CLIP, where people basically show that these models are robust because they don't use very much task-specific data.
Fascinating. Yeah, it's a really interesting point that in the limit, the kind of instruction following and RLHF that that is kind of just training, but it's another form of training, and then you can kind of figure out where you want to put those dollars, whether it's in the upfront training or RLHF or the instruction following. But yeah, that's fascinating. I guess pivoting kind of towards the your broader research, like are there other projects or like what's most top of mind for you and your research group?
Yeah, so there is a big part of my group that's interested in like kind of understanding, building all of the tools, like the Alpaca group and so on are interested in like building the tools so we can understand and study the systems. That's one part. The other part of other parts of my group are interested in essentially, maybe I would call it control. Very recently, we're interested in things like how can we make sure that models, very precisely follow instructions, or if I'm a model designer and I want to make sure that my model follows very precise controls. Like let's say it never says something that's like offensive, or maybe it's, I want to keep everything short. How do we make sure that models can sort of follow these kinds of controls? We've worked on things like using diffusion models for language in the past to basically try to do that. Diffusions are continuous, so they're hopefully easier to control through gradients. The image generation people have done really great work with putting controls on top of diffusion models. So we've studied things like that. We've also studied things like consistency for control. So consistency means if I ask a model to generate something that's short, hopefully if I ask the model, is this short to the output, it will say yes, right? So the model should be consistent, acting as a discriminator and as a generator. And we've been studying that form of consistency. And somehow, language models, not as consistent as you'd hope on these very basic kinds of queries. And so by improving that, we're able to basically get slightly better controls on these systems. So those are the kinds of things we're kind of interested in. One side, understanding, and the other side, like using that understanding for control.
That's super cool. Yeah, I feel like control and these models kind of doing what people expect has been a really hot topic, especially in the news. Where people talk about like, oh, the AI is running wild, or can't be controlled. I guess what types of you talked about like controlling the length of the output, or like what have you and your research group found when it comes to kind of coercing these models to do what is intended, and like how easy or hard is that to do, and maybe it depends on the type of model as well.
Yeah, what's kind of interesting to us is if we're trying to apply, a lot of these kinds of controls, things that require look ahead seems to be really hard for models. So if you want to, basically say like start at this sequence and end at this sequence, and you have exactly 15 tokens to make that bridge, those are kind of hard tasks for these models. Like language models right now they're one token left to right, and so it's very hard for them to do planning in that way. Those kinds of tasks turn out to be the hardest, sort of technically. And what that kind of means is, we've in the past found that like long range planning is hard. People have come up with ways of getting around that, like making an outline first and making them right. But those are kind of things that I think are going to remain challenges, like long range dependencies and planning and constraints that apply over those.
One other thread of your work that I think is quite interesting is I guess you guys had published this kind of like opinion QA paper, right, where you were essentially looking at the extent to which these models agree with different opinions, and kind of the extent to which bias creeps into these models. And I think it's really interesting, right, because obviously the folks that are doing reinforcement learning and how you do reinforcement learning can really inform what these model outputs are. And so maybe to start, I'd love if you could just kind of explain to our readers, our listeners, that work. And then, we'll ask some follow-up questions from there.
Great. Yeah, so Opinion QA was this work where we were originally asking a little bit about, let's just call them like opinions that are reflected or values that are reflected by language models. We know that language models can certainly be biased. You know, people have talked about racial stereotypes and stereotypes in general by these models for a long time. But there's also much more subtle things that these models pick up. Like if we ask them to write an essay about gun control, like will it be generally pro-gun control or anti-gun control? Unlike cases of, say, racial discrimination, there isn't necessarily a right or wrong answer here. And I think that makes it very interesting because it means that there's no clear solution to this problem. And we wanted to understand like what are language models today doing? Like what kinds of people are they reflecting? Because when they're trained on the data from the internet, that's a mishmash of many different people that have ever written text. It's going to mimic those people in some way, and that's going to come out on the other side. And so we wanted to try to interrogate these systems and see what exactly it was reflecting. And the thing about Opinion QA is we wanted to understand it in this sort of nicer quantitative way. We wanted to say like who exactly is these models reflecting. And so to do that, what we did was we took public opinion surveys from the Pew, so that they have multiple choice questions asking about support for gun control or support for surveillance, things like that where people might disagree, and they have demographic information. So people throughout the United States, like how do they answer these kinds of questions? We took those same questions, we posed them to the language model, and then we took the distribution of outputs from the language model, compared them to the distribution of outputs from people, and that allows us to do an analysis of what kinds of groups of people are closest to the language model in terms of their opinion agreement. And our highest level findings are that language models don't reflect people super well. Mostly the base language models, reflect a really mishmash of opinions, some conservative, some independent, some liberal, generally lower educated and lower income. And when there's this instruction tuning in RLHF that happens, you start to see a shift towards like higher educated, higher income, generally more liberal opinion viewpoints. And we thought that was kind of an interesting sort of observation.
Totally. And so, I think kind of begs the question of like, how do you think that these foundation model companies should be solving for this? Like if you could wave a magic wand and change the process completely, like what's the right way to kind of better reflect, general views?
Yeah, I mean, in some ways, I'm going to punt on part of that question. So, you'll have to forgive me for this. But I think one of the answers, of course, is personalization. Like it's unclear what opinion a language model should reflect by default. Like, what does that even mean? Like, is it the population of the US? Is it the population of the globe? Is it population of people in California? There's no good default there, right? I think OpenAI is currently taking the stance of just don't answer anything that's even potentially opinion-laden. That's a reasonable path, but it's also very difficult because many queries could potentially have some opinion injected in them. It's very difficult to, purge all of that out without making your language model useless, right? The language model might respond by saying, oh, this could potentially be opinionated. I'm just not going to answer it. The other paths that exist are personalization. In the paper, we also tested things like, oh, could you prompt the language model by saying, pretend you're a Democrat? Can you pretend to be a Democrat in answering your questions? That does help, but it doesn't solve the problem. And personalization, I think this is the part where I say I'm not going to fully answer the question, gets at this really thorny question of what kinds of speech are allowed, right? If we think about social media, we have the same problem, right? Of allowing people to sort of personalize their feeds, personalize the kinds of content and speech they consume. But then there's also this really thorny moderation question of like, what's the limit of that, right? Like, are you allowed to have a bot that is essentially like a neo-Nazi opinion bot? Like, currently on social media platforms, that will get moderated out. We're going to go through the exact same debate with large language models. And in a way, I think, hopefully the social media debates, in some sense, figure out some standards for this, because it's going to come for the large language models too.
I mean, one thing I'm struck by is like, so much of your work is fascinating at the cutting edge of like what these models can and can't do today. And I'm wondering how you think about, like, obviously you're doing this in an academic setting. Even as you like think about the work that you take on, like, how do you think about what makes sense to be taking place in academia versus like, the folks at OpenAI or Anthropic doing, and like, where does kind of academia fit into, I guess, the broader research that's being done around foundation models?
Yeah, I mean, I think one of the advantages of academia in some sense is our incentives are very different from the incentives of a company that's essentially trying to push the limits by building the next biggest and greatest language models. I'm sure, all of the people building these systems have the best interest of hopefully society at heart. But in general, hopefully they're trying to do the right thing. But at the same time, they're constrained in the kinds of work they can do by their incentives. Like I think the work that we're doing in terms of, trying to figure out like what kinds of opinions are in these LMs for, essentially better public discourse about thinking about what kinds of opinions the LM should reflect, the opinion work, as well as Alpaca Farm, which is really very much not about pushing the limits of capabilities today, but sort of like stepping back and saying like, okay, can we make it possible for many, many other people to get in on the kinds of language model research so we can, have a much better diversity of opinions, explore many different ideas. Those just aren't really in the incentives of these large companies. So I think academia, in a way, because of, our very different incentives and the very different place that we occupy on the compute landscape, in a sense, I think have very unique things to offer. I think things like compute efficient training, compute efficient inference, things like simulation from our group, those are all, very much informed by the fact that we operate at a much lower compute budget and we're not pushing the limits of performance.
Yeah. And so then I guess, the converse of that is there a set of things that, you guys maybe brainstorm that you could go after in your lab, but then you're like, what, maybe this makes sense for the industry to go after, or like, how do you think about the boundaries of where maybe, hey, we're not the best fit to go do this?
Right. I think, the thing that we're clearly not the right fit to do is building artifacts at the cutting edge, right? Like I think, building something that competes with GPT-5 or, whatever is not really a thing that makes sense either like technically or incentive wise for us. We do think about questions that are compute intensive, but often those discussions is there sort of a clever way around what seems like a underlying compute limitation? So we've thought, for example, about improving how we do pre-training data collection or data curation. And those discussions are like, okay, we're not going to be training a big pre-trained language model. Is there really compute efficient ways of testing those hypotheses using, say, like scaling laws or other kinds of ways of doing experiments at the small scale? And so those questions we ask are very different. So even for some of those questions, we're asking like, can we do it compute efficiently rather than let's just brute force it?
Yeah. I mean, and also obviously, part of your role in academia, you're obviously teaching this next generation of folks, and I believe you're teaching, advances in foundation models. So I can imagine you've got a fair amount of enrollment in that course, given the excitement. But I'd be curious, like, well, one, I feel like Stanford's always been kind of on the cutting edge of a lot of this stuff. But what you're kind of seeing on campus today, with folks and their interest, and then two, how you think about teaching a course like that, just given how rapidly things are moving.
Yeah, those are great questions. Things that in some ways we struggle with as well. We taught foundation models last year and we taught it this year, and the enrollment was quite different between last year and this year, as you might imagine, with things taking off. And in a way, it's interesting. The kinds of final projects that we got were also quite different. Like last year, a lot more analysis, like capabilities, like our language model is actually good. And this year it was a lot of application projects. It's like I made a language model that can order food by calling something up or calling up a restaurant, like that kind of a, let's build things spirit. And, you were asking about students, and there does seem to be a lot more of that now, of like a lot of energy also in like a lot of like, what can we do with this kind of questions? And in some ways, I wish people would think more about, the fundamental science, but I think it's inevitable that with this exciting new technology, people want to build things. And teaching, that's right. You asked about how we think about teaching something that's so rapidly moving.
Totally.
That is something we have struggled with. This year we experimented with doing a lot of guest lectures, bringing in people from outside doing great work, especially in industry, to expose our students to that kind of work that's being done. I think the course is still, in some sense, in flux. I think we're now going to try to have 2 smaller courses, one that's maybe more guest lecture oriented on the cutting edge, and another one that's more like fundamentals, like how do you train a language model, like do everything at the low level, build it from scratch kind of a course. And we're hoping to have like a fundamentals course and like a cutting edge course, and hopefully the cutting edge course can evolve and the basics course can remain the same.
Yeah, I think it's so cool that you guys are, teaching this stuff to students so quickly because, as you were mentioning, it is changing really fast, and I feel like that's something that Stanford's always done an amazing job of, is offering courses that are like the state of the art right away, because it is something that's top of mind. One thing I was thinking through was, I can imagine there's a lot of interest in AI from people, obviously the computer science students, but I would imagine even, a broader group of students that is interested in not just how these models work, but maybe how they interact with them, because they've started using them in their daily life and may touch a lot of products that they use as well. Like, how do you think about kind of teaching people, maybe how to interact with these models, but also how they work, and, for kind of maybe technical or non-technical audiences?
Yeah, I think that's going to be like a really interesting challenge that's sort of going to come up next. Like right now, as far as I know, all of the pedagogical material we have is towards very CS people. Like, how do you build it? Like, how do you do the cutting edge? I think as some of the systems stabilize a little bit, I think it'll be easier to teach sort of a how do you do things with these systems kind of class. I think the one challenge is the field and the models and the artifacts and everything are changing so fast that it's kind of hard to offer something that feels lasting and valuable. If we have like a, I don't know, chat GPT prompting class, I'm just making that up. And, GPT 4.5 comes out and you don't have to do prompt engineering anymore. That feels like a very wasted effort in a sense. And so I think for that side, at least I am sort of waiting to see how it shakes out a little bit. Like in terms of the application layer, what is the lasting interface and what is the lasting challenges that we're going to face? B, that we can design a meaty course around, rather than being a collection of hacks that we have here today.
Totally. Yeah, that makes a lot of sense. Awesome. Well, we'd love to move to a quick fire round, if you're open to it. Maybe to kick it off there, what's one thing that's talked about a lot in AI that you think is overhyped, and one thing that you think is underhyped?
The hype questions are a little hard because some people might say everything's overhyped, grunkier people. But I think maybe one thing I think is there's been a lot of, discussion and credit attributed to transformers, the architecture. Of course, it's like the architecture to use today. But I think there's been sort of almost a mythical property attributed to them. Yeah, transformers do X, Y, and Z. But I think we've seen in the last few years, there's some work from like Chris Ray's group here, or like the RWKV stuff on like recurrent nets, like starting to look good. Subjectively, this is just my opinion. Probably transformers are not the end game. So to me, it really feels like a lot of the discussion around transformers seems a little bit, a little too overhyped in terms of what it can do and how critical it is to the success of the field right now. Clearly, if you're going to make something today, you're going to make it with a transformer. I'm not debating that. But in terms of, whether it's needed, I think there's a little bit of a hype there. What's underhyped in terms of language models? I think it depends on the people you're talking to. I look at the open source community and some of the safety discussions are a little underhyped. There's been probably a couple dozen open source instruction data sets being built. I think there might be 1 or 0 safety or like, data sets for preventing like dual use, like misinformation or like toxic outputs. There's very little interest in that in the open source space. And while for like hobbyists, maybe that's okay. For this area to get more serious and like be productionized and like be used in enterprise, there needs to be a lot more work there than what exists now. In terms of the academic space, I think something that's kind of underhyped is sort of making artifacts that kind of can actually work and interact with people. One thing that we sort of realized with both Alpaca and AlpacaFarm is that there's a really big challenge between, say, like pushing benchmark numbers, which you can do in many different ways and like produce improvements, and actually trying to build like robust, usable systems that can be used by other people. I think in a way, the University of Washington group doing things like quantization have done a really amazing job at, building things that other people can use. And I very much kind of respect that kind of work where they're not just writing academic papers, but they're also able to provide something that other people can really use. And so that's one thing that I'm trying to keep in mind. I haven't really succeeded at with all of my works, but trying to sort of go one step extra than sort of the basic academic work and being able to produce things that are of value to sort of a broader community.
On your point on Transformers potentially being overhyped, I think there was like this very publicized bet between Jonathan at Mosaic and Sasha at Hugging Face on whether Transformers would be, the state of the art. I think they said January 1st, 2027. Where do you fall on that?
2027 is a really long time. So, I mean, I think if I were forced to make the bet, I would maybe bet on not Transformers, because I feel like the field could completely be different. And just like we would be working on something totally different. And I don't really know what it would be called, but there would be like the octopus model, and it would get transferred back to the language model or something. Right? 4 years is just an incredibly long time in this field, so I would just bet on like things will be different by default.
Totally.
But I do think there's a truth to it that like winners keep winning in this field because there's a coevolution between like the hardware and the models and the optimization that we do. So like the first movers in terms of like the architectures and optimizers, they end up being sticky because of the amount of like incredible optimization that happens engineering wise for them. And I think one underappreciated thing, maybe this goes in the underhyped thing, is the importance of compute for all of this. I mean, now I think everyone's coming to grips with the importance of compute, but it's not sufficient to have a good architecture. You need to have a good architecture that's compute efficient because everything now is like in compute matched settings. And so I think Transformers might keep winning for that reason. They're just, NVIDIA is going to make the Transformer GPU, and then no one's going to be able to dethrone Transformers.
No, it's a really good point. I guess for the next quick fire question, this one feels a little ridiculous because I feel like you already do so much with research in your lab. But if you could clone yourself and have, twice as much time and run an entirely separate lab, what else would you, what are some top research questions you'd love to go spend time on that you just don't have time today to do?
Oh my goodness. That's in some ways a hard question. This is completely speculative, I guess. Almost by definition, it's work that I wouldn't be doing, so it would be a little bit outside of my field. But I think a lot of the work that's happening in security for large language models is truly fascinating. I think, the work that's happened in prompt injection through tool use is really amazing and cool. The kinds of work that's happened with data poisoning on internet scrape data sets is really inventive and really interesting. I'm obviously not a security person. I've worked a little bit on people who want or who have been doing a little bit of security work. But I think it would be lovely to explore those kinds of areas. I think it's going to be incredibly important and incredibly rich, given how hard it is to get language models to do the right thing. It's going to be even harder than computer security. There we have formal models, and we still can't secure our computers. So.
Totally. I was wondering if you were going to, obviously since you started your career on the biology side, I was wondering, if you're ever going to make your way back to that, or kind of what you think of, the early efforts of folks, applying foundation models in that space.
Oh, I think they're really exciting. In a way, I feel like it's amazing that those systems work really well. One of the earliest things I did in my PhD was I wanted to make Word2Vec for the genome. I spent maybe a little bit too much time trying to get that to work at the time. But now there's been a lot of really incredible work on protein language models and genome language models, and they're working and they're producing really exciting results. In a way, I think, I'm too far removed to be able to make valuable contributions to that space. But I think it's really great to see that those kinds of things can work. One of the things that I felt, one of the reasons why I ended up not continuing on in computational biology was it felt like it was really important to be able to actually do the experiments or to partner with someone that really tightly to be able to do the experiments at the time, because the computer scientists were generating hypotheses and they have to go to the lab to basically get verified. And now maybe there's, with all these language model things, maybe there's a lot more purely computational work to be done, and that's exciting to see.
Awesome. And then I guess last question, where can people go to follow your work and learn more about what you keep tabs on what you're doing at Stanford? Yeah, great.
The best place probably is a combination of the places where we've been posting blogs, which is, the CRFM blog, as well as, Twitter. I guess it's kind of weird to be advertising my Twitter, but Tatsu Hashimoto, I generally only advertise my students' work. So if you want to follow my work, feel free to follow me. That is the place where I'll post things.
Amazing. Well, Tatsu, thank you so much for joining us. This was absolutely fascinating. And to steal a line from Jacob, I think we would be doing a disservice to the future of ML and ML research if we kept you any longer. So I really appreciate you taking the time.
Thank you very much. I appreciate it, and I love that it's very research focused. It's refreshing to be able to have a conversation about this kind of thing.